Alright, so today's topic is a bit difficult. It gives a lot of first-time organic chemistry students a lot of trouble. It is the prediction of substitution versus elimination mechanisms, which I'll refer to as competition for the remainder of this lecture. Okay, so let's consider a few substrates. So say this one, and these two as well. So one of the most important parts when you're deciding between substitution and elimination is figuring out which ones are even possible of occurring. So over here, remember one of our conditions for beta elimination is the fact that there must be beta hydrogens to our leaving group. So if our leaving group is going to be this halogen for now, if we're only going to look at haloalkanes, we'll consider this leaving group, and we'll look at the locations adjacent to the carbon bearing the halogen. So our beta position will be located here. Now, there's no beta hydrogens here, there's no beta hydrogens here. I chose these three compounds because there's actually no beta hydrogens anywhere around the leaving group. The other difference is that if we're looking at the electrophile, or what we're referring to as the substrate, then this carbon right over here is a primary carbon, this is a secondary carbon, and this is a tertiary carbon. So let's look at substrates that have different degrees and have no beta hydrogens. Okay, and the important part here is this helps us narrow down the odds. So usually we have the choice between SN2, SN1, E2, and E1. But if you look here, since there's no beta hydrogens, this makes E1 and E2 impossible on any of these three substrates. Okay. What about over here in the primary? Well, we know that the SN1 reaction or mechanism runs through the carbocation intermediate. Well, that makes it impossible here because primary carbocations are so unstable that they actually don't exist. Likewise, over here at this tertiary electrophile, SN2 is impossible because the antibonding orbital over here is very, very hard for any nucleophile to reach. So SN2 attacks are impossible upon this carbon right here. What that does is it makes the only thing possible at this end an SN2 reaction, the only thing possible at this end an SN1 reaction. Now in the middle, that's where we actually have to do a little bit of thinking. SN2 can still occur here, and SN1 can still occur here. At that point, we need to look at other factors. So you've done enough E1, E2, SN2, SN1 reactions, you should be able to start predicting what happens here. So again, I'll give you the secondary substrate because that's the only one where different things could happen. You should pause the video and try to figure out what happens in this reaction. Okay, I'm going to assume you gave it a try. So in the top path with the sodium cyanide, what will happen is we'll go through the SN2 mechanism. The reason because sodium cyanide is actually a pretty good nucleophile. So even though this is hindered over here, it will still be able to reach in here and do the SN2 mechanism. On the other hand, over here with water, water is a bad nucleophile. So it cannot go through the SN2 mechanism. Instead, it will have to go through SN1. So this will break off, creating a carbocation here, which will then go through an alkyl shift, putting a carbocation at this carbon right here. Afterwards, the water will attach, and it will go through the deprotonation steps that we're used to seeing. So let's define, for a second, what a good nucleophile really is. Well, for one thing, we know it is going to be charged. A bad nucleophile, in general, will be neutral. Okay? Now we can get more particular, but for now this will be our working definitions. Okay, so let's look at another sort of complicated system. So let's check out these two molecules here. I've already put these in their chair conformations. So what do we know about what's going on here? Well, the first question is, are there beta hydrogens? Well, they're invisible, yes, but they are still there. So this is at the beta location. This would be an example of a beta hydrogen, because remember the beta hydrogens are always one spot away from the carbon bearing our leaving group. So both of these do have beta hydrogens. Now, unfortunately, if you remember from the E2 video, neither of these have anti-periplanar beta hydrogens. So remember, in the cyclohexane ring, the beta hydrogen must be diaxial to the leaving group. So since this is axial and both the invisible hydrogens that are located anywhere else, like here and here are equatorial, they are anti-periplanar. And over here at this location, there are no beta hydrogens available. So we have an example of a substrate that has beta hydrogens, but they are not anti-periplanar. What that means is that over here on the left, E2 is impossible. And on the right, E2 is also impossible. Because remember, for the E2 mechanism to occur, the beta hydrogens must be anti-periplanar. And we know this electrophile is secondary, and we know this electrophile over here is tertiary. That actually also tells us another piece of information about this molecule. We know that since the electric field carbon is tertiary, we know that SN2 is also impossible. Okay, so that narrows down our choices just a tad. But let's try to, once again, figure out what's going to happen. So, given a molecule like this, and I'll bring the facts that we came up with over here, I want you to predict what each of these reactions will give. So pause the video and give that a shot. Okay, I'm going to assume you gave it a try. So again, because E2 elimination is impossible, the only options are E1, SN1, and SN2. Okay, in this top path over here, we have again sodium cyanide, which we mentioned before is a good charged nucleophile. So what will happen is that SN2 is still viable here since this is just a secondary carbon, so you could do an SN2 attack there and get this as your product. Now, the tricky one is deciding between these two, because we know that both in both these situations, methanol, so methanol is a bad nucleophile, because again it's neutral, and a bad base, also as a result of being neutral. Over here we have methanol participating as the solvent. So methanol has hydrogen bonds, we call it a protic solvent. And over here, on this side, DMSO is our solvent, so it's an aprotic solvent. I'll try to spell that right. Okay, so we know because the nucleophile is pretty weak, it's going to be between E1 and SN1. But which is it going to be? Well, let's think about it. Over here, with the protic solvent, with methanol acting in excess, we are going to get the SN1 product, which means this will come off, generating a carbocation, and since this is secondary and this is tertiary, there will be a hydride shift, putting the positive charge at one of these two locations. It's symmetric, so it doesn't really matter. Afterwards, the methanol will add and undergo the deprotonation steps, as usual. And the result will be this molecule and its diastereomer. So let's rethink what's going on here. What I said was methanol will add, but when methanol adds, it will add like this. Because remember, this oxygen here will be the nucleophilic oxygen. Okay, so let's visit the product of this reaction first. So if I use my solvent as DMSO, which is polar aprotic, and I have trace amounts of methanol, the only thing that can occur is the E1 pathway. Again, the way it'll occur is this will come off, generating a carbocation, there will be a hydride shift, and then once it's here, the double bond can occur either here or here. There's no preference really, so both of them will occur. Okay, so why did E1 occur here and why did SN1 occur here? Okay, so suppose over here we had in the polar aprotic solvent the methanol adding. The problem is the polar aprotic solvent, well, let me write this down. Polar aprotic cannot do deprotonations, which means that this methanol is stuck adding on here, but there's nothing here to take this H off. If there's nothing here to take this H off, it's highly likely that this reaction will be reversible and you'll get the methanol back in solution with your original molecule pretty much being there, or having carbocation regenerated here. Now that carbocation has been regenerated, the only thing the methanol can do is do a deprotonation at one of these two locations. So the reason why E1 is occurring here instead of SN1 is because over here with the SN1, if methanol is in excess, you could just have methanol able to do the deprotonation at this point, allowing the electrons to go over here and allowing this to become a stable product. So again, that's a key point. Key point. Protic solvent allows for deprotonation after addition. Let me pull that up. And remember, when the weak nucleophile is adding, you need the deprotonation to occur. Otherwise, you're going to forever have a charged substrate, which is pretty unstable. All right, so that was pretty subtle, but we'll do some more problems, and hopefully you will start to see where that's coming from. Okay, so let's look at the other molecule that we had before. So in this case, we have this. And let's pull down some of the information that we came up with over here. Okay, so once again, I want you to pause the video and attempt to figure out what will be the product of each of these reactions. Okay, I'm going to assume you gave it a try. Now, the difference is that this is now a tertiary electrophilic carbon, so it's unable to do the SN2 reaction. So over here, since this is a good nucleophile, it doesn't even matter though because it can't attack here. So it needs to wait for the chlorine to come off and the carbocation to be generated at that location. Then the nucleophile can attach. Over here, with the methanol and the low concentration of methanol and DMSO, we have similar thing happening as last time. With the Protic solvent and the poor nucleophile, we have the SN1 product. And this is again called savolysis because the solvent is both adding and then doing the deprotonation on itself. Over here, because we have an excess of aprotic solvent, we're unable to do that deprotonation step, and we're stuck with the methanol being forced to do the only thing it can, which is the deprotonation at a different location, causing the elimination to occur. Okay, because once the CLs come off, the methanol could add, but then it'll come back off, and then it'll do a attack on the hydrogen nearby. Or the CL will just come off, and the methanol will do an attack on the hydrogen nearby. And remember, the DMSO has the same exact problem, even if you had, say, acetone, which looks like this. Right, you might think acetone is somewhat nucleophilic. So say acetone uses its lone pairs to attack the carbocation that's formed. Well, it has the same problem. Once it attaches, this oxygen will become positive, and there's nothing it could do. So it'll actually, if it adds, just go back, do the reverse reaction and go back into solution. Okay. Let's look at stuff you are more used to seeing. So this will be probably significantly easier. So let's look at this molecule. So it's just a run-of-the-mill, everyday alkyl halide. This time it's simple because it has beta hydrogens, right? At this location there's a bunch of beta hydrogens, and because it's a sigma bond and a free chain molecule, these are all able to rotate around. So any of them can be anti-periplanar to our leaving group. So I want you to pause the video and give me the products of these two reactions. Okay, I'm going to assume you gave it a try. So the first one is pretty easy. Sodium cyanide is a great nucleophile. So it's simply going to attack the primary and give you the SN2. Now, if we use something like TP dioxide, that is a poor nucleophile but a great base. So So what will happen is the E2 elimination will occur, and because this is terminal, we don't have to worry about the Zeitzer-Hoffman product. The only elimination that can occur is abstraction of this hydrogen over here. Okay, let's try another one. So pause the video and give this one a shot. Okay, so by now hopefully you've realized that we need to analyze what is going on with the system here. So the first question is always, are there beta hydrogens? Okay, if this is our leaving group, then we have beta hydrogens here, and we have beta hydrogens here. Due to the rotation of this free chain molecule, any of these beta hydrogens can be anti-periplanar, and you could use a Newman projection to be able to find the arrangements that'll give you an elimination product. Now this is a secondary carbon, so things are a little trickier now. And methanol, as we talked about before, is neutral, so it is both a poor nucleophile and a poor base. But again, we're working in a protic solvent. Okay? So what's favored here is, again, the SN1 solvolysis. Let's think about the reasons why. So poor nucleophile disfavors SN2, poor base disfavors E2, and as we were talking about before, protic solvent helps SN1. So one thing you should be realizing is that E1 is pretty hard to get, but we will see an example of that sooner or later. Okay, give this one a shot. Pause the video and give it a try. Okay, I'm going to assume you tried it. This one is pretty standard. We have beta hydrogens, it's anti-periplanar, you know it's a secondary carbon, but immediately you also know that this will come across in the solution or break apart in solution to K plus and SH minus. SH minus, because of its size and negative charge, makes it a pretty good nucleophile, and we're even doing this in polarity protic, so that'll actually aid SN2. So the SN2 reaction, or the mechanism rather, will occur. Okay, next up is this. So pause the video and give it a try. Okay, this is very similar to our methanol reaction before. Once again, we have the same conditions. Beta hydrogens, yes. Anti-periplanar, well, yes, because of rotation. Water is a poor nucleophile because it's neutral, and a poor base because it's neutral. Since it's in excess, it is the solvent, and because it has hydrogen bonds, we consider it a protic solvent. So what can occur here is likely to be the SN1 solvenolysis. And here, as you generate that carbocation, what will happen is a hydride shift to the more stable location and the addition of the water to the molecule. And remember, the point of having this protic solvent is the water will add, it'll be positively charged, and then there will need to be other water molecules that do the deprotonation steps that eventually make it into an alcohol. Now, what if I told you that we're doing the same reaction, but we are going to do it in heat? Well, I'm telling you now, heat is your key word, that now we're pushing our products toward elimination. So remember from that E2 video, elimination is entropically favorable. And the equation of Gibbs free energy, it looks like this. So if elimination in general is favored by entropy, and if you increase the temperature, this becomes more favorable because G is more negative. So increasing the heat will favor elimination products over substitution products. As a result, we could actually drive this to be E1. So I got Windows help and support once again. What that will look like is you'll once again get the movement of the carbocation to this location because of the hydride shift. And then after that, you'll get the Zaitsev product. Okay, let's look at some more. So pause the video and give this one a try. Okay, I'm going to assume you gave it a try. So again, we have beta hydrogens, anti-periplanar. Beta hydrogens are a substrate. It's secondary, so it pretty much means anything goes. E2, E1, SN1, and SN2 are all viable, but here we're looking at, well, I shouldn't have said that. So again, t-butoxide is a poor nucleophile. Sorry. But it is a good base. So it's a poor nucleophile and a good base. What is likely to happen is the elimination. But remember, t-butoxide is a bulky base. What that means is that we're going to get the Hofmann product, or the less substituted double bond. Okay. Give this one a shot. Okay, I'm going to assume you give it a try. So, once again in our analysis, we know we have beta hydrogens, they're anti-periplanar, it's a secondary substrate, and this time our nucleophile, which is going to be the methoxide anion, is actually a pretty good nucleophile. So ordinarily, we would think it would go toward the SN2. But, like I said before, heat will push your products toward elimination, especially if the methoxide ion is relatively basic, and it actually is. So we'd expect here, because of the heat, a E2 or a Zaitsev product. Okay, let's change the substrate once more, just to make it a little bit more complicated. Let's say it is this. Okay, so the first thing that you'll notice is that we again have beta hydrogens. We have anti-periplanar beta hydrogens. It's tertiary, which means that the SN2 mechanism is going to be impossible. Okay, given that information, tell me what each of these products are going to be. So pause the video and give it a shot. Okay, in the top reaction, we're using a base, and it's a pretty good base. So what we're going to get is the E2 elimination, because of the beta hydrogens here, and it is going to be a Zaitsev product. In the second one, we have a great nucleophile and an aprotic solvent, which is great for SN2, except SN2 can't happen here. So what will happen is the BR will come off, and immediately it will add, because we have a good nucleophile that's negatively charged, we don't have to worry about doing a deprotonation. On the other hand, when we're working about methanol, if we're doing it in excess, just like before, we know methanol is a poor nucleophile and poor base, but it is also protic, which means it could add and then do a deprotonation on itself to a stable product. But if you have a low concentration of methanol in an aprotic solvent, then you're forcing it to do the elimination. You could probably also force the elimination if you took the methanol and you use heat. So we could also do it if we did this. Methanol in the presence of heat. Okay, that's pretty much everything. So what you should do if you're really bored is do something like this. Here I've created pretty much a flow chart of what we did here. So the first step is always going to be identifying the leaving group. The reason you need to do that is you need to look out for those beta hydrogens, because whether they're there or not determines whether or not elimination is possible. Even if they are there, well, if they're not anti-periplanar, then E2 will be impossible. After that, you start looking first at the electrophile, because the degree of the electrophilic carbon pretty much determines whether or not it's going to be possible to do an SN2 reaction on there. And then once you do that, in general, you will look at the nucleophile, and the very last factor you will look at is the solvent. So I recommend making a flowchart on your own, because that'll actually help you learn how to go through the logic of this. But I also encourage you not to read too much into this, right? So most of the reactions you're able to do by just simply thinking about it. So I wouldn't memorize a flowchart like this. I would just do enough problems to the point that you're able to intuitively figure out what you think it should